Welcome back. This is sample 2, which is really the third sample because I started with sample 0 for our force problems. So in this case, we've got Tarzan with a mass of 100 kilograms, and he is holding onto 2 vines as shown. I hope you like my artwork. I spent a lot of time on it. At any rate, this is vine 1, this is vine 2. They're both shown as being 60 degrees from the horizontal. I don't know what this is. Maybe it's Tarzan's treehouse, something like that. Who knows? At any rate, they're the same angle. So the first thing we want to do is find Tarzan's weight. Well, to find the weight, all you do is use the formula I showed you earlier. That's mass times g. Again, you can use g as 9.8 or 10. Doesn't matter to me. I don't know why, but I tend to go with 9.8. So the weight, 100 kilograms, 9.8 newtons per kilogram, because that's the gravitational field strength of the Earth. And that means that Tarzan's weight would be 980 newtons. Again, a weight is a force. It happens to be the gravitational force of the Earth that acts on something. We measure it in newtons. We do not measure it in pounds. Second thing here then, find the tension in each of these 2 vines. So this is somewhat more complicated. The thing I've got to think about here is if I have this diagram with Tarzan, so if I thought about the free body diagram, I could show something like this, where I would say force of gravity down, or the Earth down, would equal to this tension and this tension. And I didn't draw that very well either. Tension 1 and tension 2. They're at the same angle. They should be the same magnitude. And their horizontal parts should equal each other. The vertical parts of these 2 tensions up should equal the gravitational force of the Earth downward, because Tarzan's not changing motion. So if I think about that, I would write it something like this. I would say force up equal to the force downward. Well, what's causing the force upward? This tension, but only the vertical part of that tension. So in other words, this part of the triangle. Same way, this vertical tension, that part of the triangle as well. So I'm going to say T1, and how do I get this part of the triangle? Well, if I have something like this, remember back to vectors. If this is a tension, and this is 60 degrees, this is the opposite side of the triangle, so this would be tension times the sine of 60 degrees. So I would say T1 sine 60 degrees. With this one, it's the same angle, would be T2 sine of 60 degrees. What's the force down? Gravitational force, m times g. But I know T1 is equal to T2 in this case because they're at the same angle. So knowing that, I could say T1 sine theta plus T1 sine theta, or I could say 2 in this case, we found this was 980 newtons. So in this particular case then, what we could say is that sine of 60 degrees, which I'll put that as 60. When I put that in my calculator, it's 0.866 times 2, and so that I get 1.73 is 980 newtons. That tension 1, which really is the tension in both of the strings, is 566 newtons. So that's the tension in each line. So the key thing there is thinking about the fact that the force upward is equal to the force downward. And I think drawing the free body diagram also helps in that regard. Okay, this is sample 3 for our forces problems, which is really the 4th example because numbering is fun. At any rate, what we've got here is a free body diagram. And I've labeled the amount of forces on here, which a lot of times you might not actually have. So I've got the Earth pulling down with 60.5 newtons. I've got the normal force, which is the ground pushing up on the object, with 60.5 newtons. I've got an applied force, which is basically any sort of push or pull, of 60 newtons to the right. And I've got a frictional force of 22 newtons to the left. The scenario is that I want to assume a student is dragging a bag of leaves, obviously horizontally and not up at an angle, based on the free body diagram. So we want to determine the net force, the acceleration, and the coefficient of friction. So the net force is pretty easy because the vertical forces cancel out because they're balanced. So we don't have to worry about that. The horizontal forces are not equal. So all I would do to figure out the net force there is I would say 60 newtons minus 22, and that's going to be 38 newtons. And that's the net force. It's acting to the right. The acceleration I could think of going back to Newton's second law. The version of that I'm going to use is this. Acceleration is F net over m tote. So when I think about that, I just got the net force, that's 38 newtons. What about the total mass? Well, in this particular case, we've got to think about what that mass is, and we've got to go back to the equation where we think of weight is equal to m times g. The weight of this is 60.5 newtons. Why? Because that's the gravitational force. The mass is what we're trying to find. G is the acceleration due to gravity. And in this particular case, we're going to, again, stick with 9.8 newtons per kilogram. So I'm going to rearrange this, and I'm going to say mass is equal to weight over G. So that's 60.5 newtons divided by 9.8 newtons per kilogram. Again, you could use 10 newtons per kilogram. That makes the math, a little bit easier. So in this case, I'm using I get 6.17 kilograms as the mass. So notice this problem has a subproblem within it. All right, so now I plug that up here. 38 newtons divided by 6.17 kilograms. That should give me a little over 6 meters per second. So that's about 6.16 meters per second. Okay. The final thing is to find the coefficient of friction. Since this is moving, we would think about this as the coefficient of kinetic friction. If it's not moving, we would think of that as static friction. In this case, the formula is still the same. That's the Greek symbol mu I talked about earlier. Force of friction over the normal force. And so in this case, we get this is 22 newtons over 60.5 newtons. That's going to be somewhere between 0.3 and 0.4. In fact, ends up being, let's see here, 0.36. Notice for the first time this year, really, we don't have any units. Why? It's a coefficient. It's a ratio of one force to another. Newtons divided by newtons cancels out, and so we're simply left with 0.36.
Must hurt self. Must hurt self. Must hurt self. Ow! Probably better that didn't hit me.
Yes?
Hello.
May I help you?
Could you give me a little push in the opposite direction?
Okay.
Thank you.
So this is the final sample, sample 4, even though it's really the 5th example, of the Forrest problems that I'm going to be doing for you. In the PDF, I also have a sample 5. I'd encourage you to look at that and try to go through and solve that as well. So this is sample 4. Let's assume that Marissa and Spencer are part of the stage crew for theater. They must quickly move a 150 kilogram baby, grand piano, off stage by applying a force of 550 newtons. The piano accelerates at 1.1 meters per second squared. Find the force of friction on the piano. And then for the coefficient of friction on the piano. And I'm going to assume for my calculations that G is 9.8 newtons per kilogram. Again, you could use 10 if you so choose. All right, so for the first thing, I'm going to actually draw a free body diagram because it's going to help you to think about this. This is going to look an awful lot like the one in the last problem, by the way. So we're going to think of something like this. We've got F gravitational down, normal force of the floor up. You could label that force of the floor, you could label that force of the earth. We're going to have an applied force or a pushing force. It doesn't really matter what direction it is. And we're going to have a frictional force. If they are accelerating it, those two horizontal forces can't be equal. The two vertical forces, however, would be equal. So to find the force of friction on the piano, I'm going to go back to my grand equation of pretty much all of physics, at least all of Newtonian physics, and that is Newton's second law. F net equals m tote times acceleration. Well, we're given a lot of information here. We've got the mass of the piano. We've got the acceleration of the piano. So you might just think I should multiply those two together. But our free body diagram tells us something else. It tells us that we've got two forces acting there. So I'm going to rewrite this. I'm going to say F applied minus F friction is equal to m tote times A. And now I think I know everything except what I'm looking for here, which is the force of friction. Because this was given as 550 newtons minus F of F. This is 158. This is 1.1 newtons per kilogram, or 1.1 meters per second squared. So when I do that, 158 times 1.1 would be 158 plus 15.8, which gives me 173.8. So when I do this, I'm going to subtract 550 from both sides. I get negative force of friction will get me a negative value. So I can make both of those be positive in this particular case. That gives me force of friction. It's going to be 376.2 newtons. Probably round that off. So that is my force of friction. The last part over here is going to be looking at the coefficient of friction. So, thinking about that, I wonder if I should use a different color for dramatic effect, but I don't think the lighter colors show up very well on the board, so I'm going to stick with blue and black for the most part. So we've got the coefficient of friction equal to the force of friction over the normal force. Well, in this particular case, the normal force is equal to the gravitational force because we're on a flat surface. So I can go back, I can figure that out. What is the gravitational force or the weight? Mass is 158 kilograms, 9.8 newtons per kilogram. The weight, which is the same as the gravitational force, is therefore going to be equal to, let's see, 1,548 newtons, or about 1,550 newtons. And I can plug that back up here. So the coefficient of friction is equal to the force of friction I found earlier, 376 newtons. Divided by this, which is 1,548 newtons. Looks like it's going to be a little over 0.2, and it does come out to 0.24. The lower the coefficient of friction, the slipperier an interaction is. The higher the coefficient of friction, the stickier an interaction is. So those are the last examples. Hopefully these are useful to you. Hopefully you can answer the Edpuzzle questions that go with those. One of the Edpuzzle questions might be, what's the magic word for this video? Well, the magic word for this video is something Mr. McChesney at Central also is not particularly fond of, but if you ask him, you should say, hey, I hear you're really fond of this, and that's delicious ranch. If you're from the Midwest, you've got to love ranch. After all, it goes great with pizza, goes great with chicken wings. It's a classic. So ranch is the magic word. Thanks, and hopefully you have a great day.